Section 23.4, resonance in electric circuits. Resonance occurs when the frequency of a vibrating force exactly matches the natural resonant frequency of the object to which the force is applied. This is something that we saw with springs, but it also can happen with the oscillation of the electric and magnetic fields with a capacitor and an inductor. Let's take a look. So with a spring, if you have a driving force that exactly matches the natural frequency of the spring, you get this huge amplitude, much larger than you would other times. So we can imagine first stretching the spring, and when the spring is stretched, that's similar to the capacitor being fully charged. As the capacitor is fully charged, there's no current flowing at that instant, right? It charges up, whoop, and it stops everything. That's when the electric field is at its maximum. But now that it's charged up, it will start to create its own current. So it will create a current that is going around from the positive toward the negative, right? And that current will continue to increase up until a maximum point when all of the charge is off the plates of the capacitor. At that point, we have our maximum current passing through the inductor. The inductor, meanwhile, benefits from the larger the current, the better. It has the largest magnetic field possible. This is when everything is moving its fastest, which is the same part as when the mass is in the middle of the spring. It's at its max speed. Once you pass that point, though, the capacitor plates currently are empty. They're going to start to charge up in the opposite direction, right? We have these positive charges moving over here. They're going to start creating positive charges on the right and negative charges on the left. So the current will continue decreasing, but continue charging the capacitor plates up until a maximum is reached, until they are all the way charged. We have all the positives there, all the negatives there. Now the electric field is in the opposite direction. And there's no current flow for that instant. But once they become all the way charged, once the current is all the way used up, we're at the other maximum of our spring is fully compressed. It's ready to spring back into action the other way. Sure enough, we're going to see a current start to appear in the opposite direction as the capacitor discharges, and that current will increase up to a maximum, which is then a maximum magnetic field for the inductor, where the magnetic field is also in the opposite direction. You can see this with the right-hand rule. And so on and so forth, right? After this maximum current, the current will start to decrease as it charges up the capacitor plates with a positive on the left and a negative on the right until we get right back to square A, right where we started. So it's a very impressive cycle. That's when we can get the largest resulting currents out, because there's the most motion. Let's take a look, now that we've seen this conceptual overview, at what it actually means in the calculations. So what we're focused on with resonance is finding the maximum current. And the RMS current is just going to be the RMS voltage divided by the impedance, right? Our impedance is the square root of R squared plus XL minus XC. Remember, that's what these are. It's just fully plugged in here. Cool. So we have that. If we look at the RMS current, what we'll notice is that it's really small at large frequencies, and that comes from the inductance. As the frequency gets larger, the inductance starts to become huge. The impedance there is really huge when the inductance is big. Similarly, the impedance is really large at small frequencies due to the capacitor. Small frequencies, the XC blows up, and we get, again, a really small amount of current. So what we want to find is the sweet spot right in the middle, where we get the largest amount of current and the smallest amount of impedance. When will that occur? Turns out there's a way that we can minimize the effect or the influence of the inductor and the capacitor. Since they're being subtracted from each other, the way we can get the smallest amount of impedance is when these two cancel each other out exactly. In other words, we set XL is equal to XC. And if you plug in those values, 2 pi, we're going to call it F naught, which is the resonant frequency times L, is equal to 1 divided by 2 pi, that resonant frequency F0, C. And you can solve for the resonant frequency, multiply it up there, divide by 2 pi L, take the square root, and you'll find that the resonant frequency is as shown, 1 over 2 pi, the square root of LC. It doesn't depend, the resonant frequency doesn't depend on the resistance. It just depends on the inductance and the capacitance. And you can tune those to get a very particular resonant frequency out, which is very convenient. Then the overall impedance at this resonant frequency is just equal to the resistance, because XL and XC have canceled each other out. So this introduces the idea of resonance in electric circuits. I know it's a lot of terminology, but if you can keep the terminology straight, the equations are fairly simple to plug and chug away, and you'll be able to solve these AC circuit examples, which have some really weird things going on, but lots of useful applications.